Hey everyone, my name is Pramod from the CoinUp collection, and today I'm going to show you how to create an audio module. Basically, in your core, you can have several different types of audio modules that you can possibly use. Um, some of the common ones that I use are the YM2151, which is an FM type of chip, and then I use some ADPCM decoders. The 6295, which is what I'm going to show you today, is a very common type. It's also pretty basic. It's a basic type of ADPCM decoder that's used in a lot of different games. And Basically, what these audio modules do is they take data from somewhere. It could be sound data or any other type of ROM data that has samples in it, and it decodes them, and or sums them up into a waveform, and then that ultimately plays on your speakers in a digital output format. Today I'm going to show you how to kind of approach this in the way that I usually approach these types of things. Essentially, I'll show you how to organize your project, how to approach testing, a test bench, just pretty much all aspects related to creating an audio module for use in a FPGA game core. Okay, back to basics. So let's start with the data sheet. So you have a goal in mind, and you want to create a module that is based, on an audio chip of some kind. It could be a Konami audio chip. It could be something common like this one that I'm going to show you today, which is very simple. It could be a Yamaha one. It could be all different types of audio modules, right, that are out there. What is the first thing you do? You have a goal in mind. What is the first thing you do? Well, I think the first thing you have to do is decide why you want to do that, right? Because when you're approaching something in FPGA, nothing is quick. Okay, there's all sorts of problems that can pop up, and they pop up pretty randomly. Sometimes you're not gonna know what to do or where to go on that, and so it takes a lot of persistence and effort to meet that goal. And so I think the first thing you have to decide is why you want to do something, and once you have the motivation to do it, then you can only proceed forward from there. But if you're approaching something and you don't know why it is you want to do it, or you just want to kind of like randomly learn different things, I don't think that's a good goal, and I think that you'll easily give up if you face walls in front of you, right? So I just don't think that's a really good motivator to do things. So you have to really decide why you want to do something. I mean, especially in Verilog, if you want to do something in FPGA, you have to decide why you want to do something, and then once you have a strong motivator, you stick with it until you get it right. Okay, and that's what I typically do. Okay, all right, so let's take a look. The first thing I would normally do in these projects is I would take a look at the data sheet. And the reason why I take a look at the data sheet is not to focus on any implementation details. I take a look at the data sheet to take a look at some of the specifications involved, right? So the specifications are usually on the first page. I'm gonna make this a little bit bigger so you can see it. Um, it's usually on the first page of the data sheet, and it shows you like what the capacity is. And I mean, in this case, it's an audio module, right? So you're talking about the number of bits per sample. That's very important, right? 4, right? You have 18 address lines out to an external ROM. So right here, from these two statements on the datasheet, I already know that uh, each sample is 4 bits, right? So and this also interfaces directly with an external ROM, right? And there's 18 bits for that. right, that you can possibly have, which describes the maximum addressing capability of the chip, right? What's the size of the ROM, the maximum possible size you can have, for that external ROM that you're connecting to this chip to play samples, right? Um, so this is very important information because it tells me that even if I have byte addressing, right? So that's 8 bits per byte. That means that one byte fetch can actually play two samples, right? Now, the entire sample length is composed of many samples. The length of the sample is the most likely factor in determining what the size of that is. So a typical sample that lasts like a half a second to a couple seconds might be in the tens of thousands, right? Depending on what the sample rate is, right? So sample rate is something we'll talk about in a little bit when we get to the implementation. But let's keep going. So you have an 8-bit control bus, right, for your mode setting. You have external memory capacity is 2 megabits, right? Interfaces with common CPU and MPU, right? And your clock frequency, which is important, it's 1 megahertz to 5 megahertz rated. And that's pretty consistent with what I've seen. Typically, what we do from an FPGA perspective is we put the master clock into something, and then we gate that master clock with a clock enable. Now, what that means is, let's say your master clock is running at 96 or 48 or 128 megahertz, something high, right? Something fast, right? Uh, in order to achieve cycle accuracy to the system that you're trying to do, you have to slow certain bits of logic down. We call this gating the clock, right? So you want to gate the clock in a certain way. Now, what that means is, for example, if you had a 96 megahertz clock and you wanted to make something run at 48, that's effectively half of the speed of your master clock, right? And so what you do is you toggle every other cycle, right? That effectively halves the speed of your master clock, right? So you create a counter that does that, okay? So you count the number of cycles that you elapse at your master clock, and depending on how many cycles have elapsed, you are going to toggle something from high to low and low to high, right? Rising edge, falling edge, right? That's how you work out timing in an FPGA. So you're going to gate that with a clock enable, okay? And it's going to be synchronized with the master clock, and it will effectively run at that speed, okay? Okay, now let's talk about the sampling frequency, which is the next line, between 6.5 kilohertz and 8 kilohertz, right? And there's a relationship between the sampling frequency and the input clock that you provide to the chip. So that becomes very important later on. You have number of words, 127. Vocalization time, 60 seconds maximum. Okay, so the maximum possible length of a sample could possibly be 60 seconds at 8 kilohertz. Okay. And then the rest of the stuff related to power and all that stuff, packaging size, doesn't really matter. Actually, no, it does not matter because we're doing an FPGA course, so it doesn't really. Those are not details that we would be familiar, or I mean, sorry, those are not details that we would really pay attention to in the core development process because we don't usually target standalone PCBs that are custom for our stuff. Now that might come into play. Like, let's say, for example, let's say you were creating a PCB, right? And you want to put a legit 6295 on there because the core is just not accurate enough for you, right? you can certainly do that, and that's where power comes into play and all these other things, space, uh, the form factor of the chip, what size of your PCB is, like all that stuff comes into play with when you get to that world. But normally, what we do is we target mainstream FPGA platforms, like the Mister or the Analog Pocket. So those are pre-made, pre-baked systems. So we normally don't really get into that. All right. So let's take a look at some more of the data sheet. So, okay, so on the next page, you have a block diagram. The block diagram is also something I take a look at very closely because it tells me what the layout of the internal structure of the chip is. Now, it doesn't give you any implementation details, but it does give you some level of detail for you to kind of get an idea of how this chip is structured, right? So it looks like there are some registers that intake things. It looks like there are four separate channels, and the four channels go through these converters and control circuits, right? And it looks like the four channels are operating independently, and they have shared access to the common bus, right? Because look, you have the data in, right? And this data comes from the ROM, right? This is the addresses going out of the ROM, right here, out to the ROM. Sorry, so there's your A0 to A17. They said it was an 18-bit address width, right? And then you have the data which comes in, and you see that's shared among these different components at on a common bus, right? So uh, it tells me that there are two phases to this exercise. One is retrieving the sample metadata, right? So when you deal with ADPCM samples, and you can also figure this out by researching the data format, which I've already done already. What I would normally do is I would study by opening up in a hex editor. I would take a look at the PCM ROM, right? The ADPCM ROM, and I would take a look and see how the data is structured, right? And I would normally for ADPCM data, there's like a table in the beginning of the ROM that describes the layout of where the addresses are, where the samples are, and the metadata behind them. The metadata includes start and stop addresses, as you can probably see here. And what those tell you is basically uh, I'm gonna basically when a CPU interfaces with this chip and it sends a command, so they call it a command. What's going to happen is that command is going to key this chip into requesting the metadata in the sample table at a certain address. The metadata includes the start of the sample address and the stop address of the sample, right? And then what it's going to do is make another request to the same ROM and get those samples out, or start getting those samples out, and then just looping through them, decoding nibble by nibble, which is 4 bits, right? And then just simply sum them cumulatively until it reaches the stop address. Okay, and that's why there's an address counter here, right? And you see there's address compares here too, which is used to in the ROM fetching process as well. Okay, so that is, and here's your voice synthesis circuit that does the magic once a sample arrives. And then you have a busy register here, which also becomes important because um, when the CPU tries to send commands, it's very important that the CPU know the status of the different channels, right? It has to know, like, are there any free channels for me to play this sound on, or no, right? And so that's when that would come in. Okay, so that's the basic layout of this. So I definitely take a look at this block diagram very closely. Let's take a look at see what other sorts of information there is. Now, this is also kind of important. Uh, the I mean, I said this wasn't really important early on, but it is kind of important because sometimes what we do is when there are weird issues. Now, there have not been obviously weird issues that have come up with this particular chip because this chip is very well known, right? It's pretty much figured out. But there are times when chips display odd behavior, and we want to tap those on the board. Usually, we're working from boards that we own, right, or have access to, right, in our network. We're generally not working much from unknown sources. I mean, unless I mean, there are times when we do that only when we have a comparable board or something's well documented, like in literature. Like there's a lot of literature behind the system and it's well documented. Most of the time, we're not just like randomly implementing something by opening up a MAME driver or something else, some other source of implementation. Normally, that's not really what we do. We normally, I mean, that's a step in the process, but that we don't normally solely rely on that. And actually, I think if you're going solely based on a working implementation in C or some other language, that actually can be more difficult than getting the board or getting pictures of the board and taking a look at the architecture and just researching the literature. That's actually not a beginner's exercise, I think. I think you have to be very experienced to do something like that. So I suggest not doing it. I personally do not do it very much, unless I really know the system and it's maybe like a derivative of something that I've worked on before and I understand very well. Because like when you start to work on things in FPGA, you have to know a lot of low-level details. And that's not to say that you're using necessarily low-level implementation, in the actual programming, but you do have to know a lot more details than if you were to do it in C, primarily because memory access is different, the way you use resources in the system is different. It requires more details to do something like that. The speed is very important. Like when you're writing C code, you don't really have to care about the speed. The speed regulates itself in the operating system, right? You don't have to worry about like, I mean, I guess you could control it to a certain extent, but like you're not really worried about like, cycles, like on a cycle by cycle basis. Like you're not really worried about too granular levels of time. I mean, you can control the speed of something, but you can't really. I mean, you're not really. I would say you're not really so much focused on that. And plus, like, memory is hyper fast on a PC versus doing it on an FPGA where resources are very scarce, right? And you have to worry about how you're using something and how long memory fetches take and whether they fit within the component time of your system, and all that stuff. So it's not really something we worry about in C versus FPGA. So that's the main distinction. Anyway, so I would use these sorts of information to tap the chip if I need to. Most of the time I don't, but sometimes you do. The next thing I want to take a look at, I take a look at timing, the timing charts sometimes. In this case, I do take a rough look at the timing chart just to see the cycles that elapse, what the sequence of events are. Mostly, I'm using this for the sequence of events. So I'll use this to determine let's say a read is to happen. What's the process? Someone, asserts a read pin, and then 2 cycles later they get their data and it appears on these pins. Like those types of details are something that I would look at the timing chart for. Um, this is very important, the pin description, because the Verilog core that we're going for here is supposed to be pin accurate. So we want to make sure that the pins are named appropriately and that they are outputting the right things that they are supposed to be pin compatible. Okay. And here's the function explanation. So I would use this information. I mean, not all data sheets have this. I think that long ago, you tend to see a lot more implementation details in the older chips. Nowadays, they don't really give many details because of IP issues, right? I mean, manufacturers are worried about cloning and all these sorts of things, so they don't really give many details nowadays. It's becoming more prevalent. But back then, there's lots of details, and actually, you can use these levels of details to get more information about how it processes the samples. And the attenuation level is extremely important. There's a lute behind this. Um, there is the channel specifications important. So there's lots of information you can glean from this. It tells you how addresses map, what the ROM. This is what I was talking about before. The ROM structure I studied already. It shows you how the speech data is synthesized, right? Like so, there's lots of different. It shows you a timing diagram too. So there's lots of different information you can use for your implementation, and it shows you again another application circuit type of diagram that shows you how this chip is integrated in the PCB, right? You can see that the DAO pin is connected to a DAC, right, an LPF filter, and then out to sound, right, out to speakers, and then you have a ROM integration here. You have the decoder here, right, like the address bus decoder. You have your MPU, which sends the commands to this thing. So yeah, so you have this is your diagram of what, like if you were actually making a PCB that had this chip on it. This is the architecture on the PCB that you'd be going for. Okay. All right. So that's all about what I use the manual for. Not the manual, but like the data sheet for. Next thing I do is once I have a rough idea in my head of kind of how I might what the general workings of the chip are and what's the capabilities of them. The next thing I do is I search for current implementations, right? So I have a MAME one up here. That is the 6295 from MAME, and I take a look at it. Like the problem is, like I said, if you're taking a look at something like in a current working emulator and you're taking a look at the implementation detail of that, I don't think that's a beginner level exercise. I think the reason why I think that is because there's a lot of concepts in the emulators that are like kind of invented, right? That's not really that's either like that's not really existing. It has no grounding in like the actual application circuit, or is something that is specific to making it work on a target operating system, or using memory in a specific way, or data structures in a specific, especially data structures, right? Like data structures are totally different in the emulators versus doing it on an actual circuit board, right? They can rearrange the data however they want, right, to make things work. Even if it's inefficient, they can rearrange it. They can add stuff to it. Like there's all sorts of things they could do. That doesn't necessarily mean that was the way that they did it, right, on the board. It's just for convenience, because when you're making a software emulator, right, you have to think about okay, well, what's the target specification of the system, and how how much processing power does it have? Like, am I targeting like a portable device? Am I targeting, something that's really high powered that has like some crazy NVIDIA chip in it? Like, there's lots of different things that you can target, and so uh, I think depending on what you're targeting, you have various optimizations in these sorts of things. So that's why I tend not to follow the architecture or the way it does things. What I look for in the emulators are very specific. So first of all, I'm looking for low levels of details. Like this is an example of a low level of detail, right? So right here, it says that pin 7, which is the SS pin, is termed a divisor, right? And so if you have pin 7 on, then it divides your input clock by 132, If not, it divides it by 165. That's a very important point because that leads into the sample rate, right? That's how the sample rate is calculated and how the sample clock is generated by the chip, right, to play the samples properly. So if you have an input clock of, I'm sorry, not I don't mean the master clock. So the master clock is definitely going to be an input into our FPGA core, but like I'm talking about the clock enable, the actual speed at which the chip is supposed to uh, run at, right? Like which is like a 4 megahertz or a 2 megahertz, right? And then you divide that by either 132 or 165, depending on what uh, what the setting of pin 7 is, right, for that board. They're all different kinds of settings. What I take a look at, see again, there's that pin 7 again. I take a look at the addresses at which it reads from. That's a very important thing that you could get very easily from an emulator. I take a look at address bus configurations. I take a look at decoders, specific algorithms um, that I can use to get an idea of how this thing might be implemented, right? Um, so so here's your nibble. Here's that 4 bits that it's talking about. So there, yeah, I try to see how it reads data from the ROM, how it's generate, what's the algorithm of the ADPCM decoder. That's something that you can take a look at current emulation for. That's what I get out of it, and not much else really. Oh, loots, specific loots, right? This is your volume loot right here. It's very important because somebody has the people who created these sorts of emulators have already done the groundwork in the past, and they have traced out all this stuff on the board for you. If there are specific loots or data tables or reverse engineering information, you should take them from the current emulator. Okay. What else? Yeah, I take a look at the notes. Sometimes, like if I mean this is a simple chip, so I don't really have to like dive in too much. But like basically, if it was an actual game core, I would go and read the whole history of that game core because there, it's important to see like the history and the evolution of how something went from like just barely implemented to working. And I think there is a historian aspect to all this in that like if you're just focusing on the current implementation of the way that thing was done, I I mean you could kind of get by, but like I don't think that's a productive way to work it because you're gonna miss a lot of details and very important details too because like um, there are there you get to see like how knowledge has evolved in the system, right? And I think that's very important to take note of. If you're implementing something because you want to know like how something has been documented over time and what levels of detail that they added, so you don't miss those details. And maybe later on they added something and they maybe took it away because like they said, okay, well maybe this is inconsequential to the system, and then all of a sudden you have a bug somewhere and you have no idea where it comes from. And I think if you read the history of how something's implemented, 9 times out of 10, the bugs that you face when you're implementing your game core or whatever sort of core you're doing will likely have been encountered in the past and documented. So that's why it's important that you kind of read through the history of something before you start implementing. Okay, all right. So that's what I look at current emulator sources for, and I'm going to show you Final Burn as well. So I always have Final Burn open. Final Burn is my tool of choice for doing research. Now, typically, what I do is I use Final Burn to research the workings of something, right? So I'll use it to play around. It's easy. It's easier for me to compile than MAME because one, it works in Visual Studio, and I can mess around with the C code, and set breakpoints. I can print messages at the bottom and do all that stuff. Um, and I don't know. I just like it a lot better. I think it's easy to work with, and it's not very abstracted like MAME is in multiple layers. It's just easier for me to work with. So I just tend to use Final Burn. And so that's what I use. You don't have to use it, but that's what I use. And so like I usually will play around with this. Like I'll mess with this. I'll see what happens. I'll change some of the code intentionally and see if I can break something. I'll often try to reproduce issues that I'm facing in the FPGA core in Final Burn. So if I can reproduce it in Final Burn, then that means I will have understood the issue, and I know where it's coming from, and I know what bearing it has on something. So that's what I use Final Burn for. And in terms of this exercise of implementing this chip, I mean, this is a full implementation of it. I get to see like how the clamping is done and all that stuff. So those are levels of detail that I usually try to go through. Okay. All right. So once all that is settled and I have all the background information that I have, on the thing that I'm doing, the next thing is to decide upon an appropriate architecture for the core itself. So I'm going to open up the code that I have, and we'll open source this and many other things. Probably in a little bit. We have a lot of documenting to do, with respect to the readmes and usage information, test benches, and that sort of thing. But this is the implementation of the final X6295 chip, and this is the top level. And as you can see, it's pretty much pin compatible. Now, the reason why I recreated this particular audio module, is because I mentioned this in previous videos, but the output of the current JT6295 is muddy. Like, I think that it's clamped too hard, and it just doesn't sound correct. Like I mean, it sounds correct. It's correct. Like, sounds play, but like it sounds a little bit muffled. It sounds a lot muffled. And actually, when you take a look at the waveforms, I mean, I'm not like a technical audio expert or anything, but like if you take a look at the waveforms, it's very clear that the audio is clamped too much. Like, too much is being filtered out. What I want from an 80 PCM module is raw sound. I don't care about any filters. I don't care about any of that stuff. You can put like 20 levels of filters on it. And it still won't sound correct, right? It just seems like the more advanced we get in society, like the less it really sounds like the original that you're trying to like implement. And I mean, you can claim that your thing is technically accurate, and that may be true. Like, you can take all these sorts of measurements, and the fact is, the only thing that matters is one thing: what the person perceives when they hear or interact with your thing. That's the only one thing that matters. And I think that I, in terms of this ADPCM module, that was my goal. I want raw ADPCM. I don't want anything more. I want just that. Just give me that. Don't put any filters on it. Just take the raw ADPCM data, decode it, give me the sound. That's all I want. Okay, and that's what I have here. Okay, so we have the pins, which are pretty much pin compatible. I added a few things. I added sample valid, and I added sample clock as well. As well as busy voices. These are kind of debug outputs. Well, not really debug outputs. These are actually used. But like the busy voices is a debug output, for example. I've added a convenience function for PCM out. Now, normally PCM out is not a output port on the original chip. this is the actual raw PCM data that I'm looking for. Normally, applications would access the DAO port and run that through a a filter of some kind, and then and or a DAC, and then they would get their final sound, right? So that's that's something that so I added the ability to do both, right? But when you get into like the DAO pin stuff, then it means that you're going to use some of the GPIO pins to interface with some other audio device, and like there are going to be a number of pins for that, and that's just not what we're doing here. So I mean, like I I have it, it works, but I don't use it. And then there's that SS pin as well as the other pins, right? And then there's that SYN I was talking about. This is the clock. This is your clock enable, and this is your system clock. So your system clock will be higher than the clock enable. Okay. This is your top level module. So your top level is basically this. So you instantiate X6295. You connect all these pins to your current core, and then you have the different sections. So this is your clock divider, right? Like I mentioned that if it's on, then you're going to divide your thing by 163. If it's off, then it's 130, right? So like basically, this is your dividers for your clock enable. So and you see like here it's gated by SYN, right? So this many cycles of SYN will get me my target output frequency. Okay, that's all that is. All right, and this is your command status interface module, right? So this is one module, right? And basically this is your top level, and it instantiates something called X6295IF, which is your command status interface, because you have to have ability to intake commands, right? That's what I was showing you in the block diagram earlier. Like there's an interface to take in commands from an external consumer, which is some sort of CPU of some kind. And so these are the things that matter in that interface, right? And here's your ROM counter and your ROM address comparator, right? This was also discussed in the block diagram, and it's used for ROM handling, external ROM handling, right, to an SDRAM controller. Okay. Arbiter is a generic module that I created. I'll show it to you right here. So there's a dependency on one of the other modules that I created here. So this is a general arbitration module that I created long ago for Midway, because Midway, like the bus works a little differently than most systems. So what happens is each device on the bus has like fixed units of time under which it shares the bus, and it doesn't go over that time. So I had to have like an arbitrator that kind of did that, and so this what this does. So this is generally speaking a round robin arbiter, meaning that if one device gets granted and they deassert their request signal, they will not be granted again, even if they reasserted it like a cycle later. There's already another consumer who's been granted, right? So it'll rotate through fairly between the different consumers, and it works for a number of lines. And basically, it'll give a grant signal when when that particular consumer should access the bus. Okay. So that's your ROM grant, and what I do is I have 4 channels. So there's another module called Voice, X6295 Voice, which is kind of the core module. It's the heart of the 6295, because like basically you have an interface to intake commands. You interface with a ROM, you get data, right? But how you process that data and output sound is through channels, right? And there's 4 channels for this, right? So you can possibly play 4 different sounds at a time. Okay, and that's how it works. So there's 4 channels, and they all have the same logic. So that's why I'm instantiating this 4 times. Generate is a very important concept to replicate different sorts of um, logic, signal logic, different sorts of repetitive element logic, that sort of thing. So if you want to instantiate a module n number of times, or you want to instantiate like always blocks a number of times, one for each one, then you'd be using generate. So I use that pretty frequently. Okay, so yes, here's your 4, and then it's going to instantiate this 4 times for the 4 channels. The 4 channels go into the arbiter, right? So each channel can request data about a sample from the ROM, but they share that bus, and that's what the datasheet says. So that's what I'm doing here. And then we have a couple of other things. We have the busy voices that I mentioned earlier. Tells you which this is a debug output. It tells you like which channels are busy or not. This is your multiplexer for your address, because like I said, all the 4 channels share the bus, so you want to multiplex between them, which one gets access. This is normalization. So once you have your final audio from all 4 channels, you sum them together. That's your mix. Okay, so basically how most of the audio stuff works is you have various channels, and to replicate sounds on top of each other, you add them. To increase the attenuation or volume of the sound, you multiply it. To decrease, you divide. Okay. And then to clamp, you subtract, right? Or you compare, and just have a fixed value that you're doing. So this is clamping, right? This is clamping, and this is your DAO, right? Sample valid is very important, because you only want to output sounds on your speaker that are valid. Like, you don't want a bunch of static, right, or noise. You want to only instruct your code to latch data if the sample is valid. That's the way it's outputting valid noise for you. Okay. Okay. So that's the top level module, right? And then this is the command interface, right? There's not much to this, honestly. It just intakes the data from a CPU, like your DN. It supplies a DOut. DOut is really like the status of the channels, and basically it detects that. It queues an operation, and it detects, this is your mask for which voice to start, because each command that's sent by an external source can possibly play on one of the 4 channels, right? And ideally, they're using this to instruct or inform which channel they're playing it on. And this is the meat of your module, is the voice decoder, right? So there's a couple of different parts to this that I'll go over. So one are the loots. So the volume loots are taken from the current emulators, because there's a little bit of a nuance to them. So like, what's interesting is the manual mentions like 16 different levels, but you see, like, if you actually set these levels to something, right? Like, just don't set them to 0. Like, you actually set them to what they're supposed to be as per the manual. Things would be wrong in some of the games, and Basically, we had this bug for a while, which is solved by muting some or incapacitating some of the volume levels, which is interesting, I thought. And then you have your step loot. So like the way the step loot, what? Okay, so what this does is like when you're producing sounds, um, sounds are a waveform, right? So the different samples describe steps in time of where that waveform should go, up or down, right? They call that the delta. Okay. So when you're processing audio, each sample is 4 bits, right? We saw that in the data sheet. Um, each each 4-bit sample um, describes a delta from the previous sample's position, right? So all the samples start at 0. So your waveform starts at 0, right? And as you step through the different things, so you're retrieving the ROM, you're getting it, you're decoding it, and you're applying the step loot and all that stuff. You start to get a sense as to like, okay, I was at level 0. Now I'm at 2000 something, and now I'm going down to 1000, or I'm going negative, I'm going below 0. Okay, I'm going higher and lower and higher and lower, like a waveform, right, over time, right? The time unit described is called the sample clock. So the sample rate is how many samples per second would lead to that waveform being constructed, right? So you iterate through everything at the sample rate. You output samples at the sample rate. So every time your sample clock toggles from a 0 to a 1, you're going to that's your trigger to output a sample. And it's not dissimilar to video, right? Like, so video, like you have all sorts of video timings. I mean, if you were to compare audio to video, like you have all sorts of video timings. Like you have the V blank, you have the H blank, right? You have H sync, V sync, right? Front porch, back porch. There's all sorts of different video timings, right? But ultimately, right, when you're doing video, like let's say you're trying to output a video frame, if you're taking a line buffer approach, you must output the successive line by the time H blank reaches the next H blank. So by the time when you start the horizontal blanking interval, if you're not able to output that the next successive line by the time the next horizontal blanking interval occurs, then you're in trouble, right? The same thing is true with vsync, right? So vsync determines, I'm sorry, vblank determines, what, uh, where your frame cutoffs are, and vblank is a very important concept in, especially in these types of retro games, because often things are timed at vblank, right? Because that's your one frame cutoff, right? You create animations on a per frame basis, right? And so when things occur are often timed to when the frames are outputted, right? Your frame rate, right? When vblank hits, that usually signals and usually there is an interrupt for vblank, and what it does is it signals the program, the system program, to start staging things for the next frame. And so like you use that information to kind of start processing stuff for the following frame. Okay. So it's kind of so it what I'm getting at is it's sort of the same as audio, right? So audio, the V blank. Actually, I would say like probably the H blank of audio is the sample clock, right? So you must process all of your data and output one sample by the time the sample clock occurs. Okay, your sample clock is your trigger. Okay. Okay. So in order to do that, so we have the step loot. We have a decoder task, right? I use tasks pretty often in Verilog. I don't know that you if you use them or not, but like I use them pretty frequently, and the way I use them is to organize repetitive things. So normally, tasks play a different role in simulation versus in a synthesizable model. When you have a task, what happens is in synthesis, and I'll show it to you below, but like basically it takes a copy of this, and you also get temporary scoped. It has scope too, so you can get temporary scoped variables. But like basically, it'll take the contents of this roughly and inject it where you call it. So it becomes very easy to create repetitive logic. That is like this. I mean, you can see how this is useful in a test bench, but you can also see how this is useful in you know regular operations too. Okay, so this is these are the decoding stuff, and I split it into two different parts because like some of these have multiplication and all that stuff. Like you ought to be very sensitive about like lots of different addition operations chained together in combinational form. This is a lot of this is combinational, and multiplication in FPGA because that could blow up your timings, right? So I had a timing issue with some of this all being in one cycle, so I split into two cycles. Um, and then you have your stop handling, like because let's say you're playing some sample and the program wants you to stop, right? What do? You don't keep playing it; you stop it immediately, right? So that's it. And then I have this as well. So this is what I was talking about. Like the sample clock is the H blank of the sound world, right? This tells me when I need to output a new sample. I must output a sample when this toggles high. Must. No exceptions. If you don't do that, your audio will be screwed up. That's all there is to it. Your audio will be screwed up. Okay, and this is the main state machine that processes all this stuff. So the first thing that happens is it gets the metadata of the sample. I mentioned that. So it takes the sample number and then like it's very similar to tiles. Like if you have a graphic system, like you have a sample number, the command describes the sample number. Tiles are the same way. There's tile IDs, sprite IDs, object IDs, that sort of thing, that you use to calculate your address of where they're located, and that sort of thing. So yeah, it's pretty similar. You have your ROM address. Um, you assert ROM CS to indicate that you want to fetch something that will go to the arbiter. The arbiter will grant which of the channels comes first or whatever have you, and then you go access the bus. You get the ROM data out. Once you get the ROM data out, there is a specification of how the table is stored. That's this. Start and stop addresses, like it showed you in the datasheet. And then basically you keep iterating through that, iterating through the table until you get all the metadata. Then you basically can it, and then you go to the next phase, which is your starting position of when you play. Where the sample starts is the start offset that we got from the metadata. And then it goes in a loop until the sample ends in a state called playFetch. What playFetch does is basically it starts playing, it decodes and also processes the samples. So where it processes the samples is at the ROM level. So I'll show you that here. You see here, I have my tasks. Decode nibble B, decode nibble A. I have my pre-decode 1 and pre-decode 2 triggers for when I'm supposed to run them. So basically, it's like a pipeline. I will get 1 byte when the sample count is even, because each byte covers 2 samples, even and odd, right? The even and odd nibbles, right? So basically, if the sample count is an even number, I will go fetch new ROM data. And well, in this case, I'm doing it on the odds because I pipeline them. But like basically, one even would cover both samples and that sort of thing. And then after that, I convert the ADPCM data to Q to the integer form, right? From the this fixed floating point format, and then I increment sample count, and I do it all over again. So this loops until it reaches the sample threshold end, and then it issues a stop, and that's the end of the pipeline. So that's that, and the actual ADPCM decoding logic is mostly from current working emulators. That's something that you can get, like I said, specific algorithms or something that you can get from current working emulators. And that's how I process these things. Um, and that's about it. That's a good overview of this sort of the module, right? And how I put together all this information. Now let's talk about the test bench for a little bit. So the test bench is right here. And there's a couple of different things you want to do with the test bench. So one is I use this test bench for multiple purposes. I don't use it to verify the functionality of what I did, but rather I use it to investigate issues with particular samples. So for a while, when I created this, like I would have very specific issues with certain samples across various games. So that's what I use this for. I use this to research samples, and what I can do is I can supply the ROM for the ADPCM data, and this will auto decode them for me and use them as if it were the actual core. And there's a couple of different parts to this test bench. So one is declaration of the signals, the clock, right? So I was the last time I was researching something was Batrider, so it's 94.5 megahertz. Then you have your clock enable. This is 3.2 megahertz. You have your ROM. This is the ROM loaded in initial, right? So it loads this is basically a hex conversion of my ADPCM data to a hex text format. This is the ROM interface logic. Again, very simple. Doesn't need to be speed accurate, just as long as the data gets to where it's going. And there's banking too. So like the Batrider used the NMK 112 for the banking because, like I said, you only get 18 bits for the ROM size, right? Obviously, you want to store more sounds than that, right? So if you want to use more sounds than that, you need some external banking mechanism. So I just put 5 as the bank. That's where the particular sound I was debugging, that's where it comes from. Spank 5. This opens up a raw file. It creates a raw file that's used to store the data, the raw audio data. And I'm only outputting data to the file when sample clock hits. And there's actual data to be processed. Not every time, because otherwise you'll get like blank noise, right? Not just sample clock, but sample clock and also busy voices. So there is a channel playing something, and also the sample clock hits. Okay, and this is my task. Like I said, I use tasks very often, right? And what this will do is includes all the steps for submitting a command to the chip. I extract the commands that I use from emulators. I'll show you how to do that real quick. So let's pull up a game. Let's say Truxton. and what I'll do is, you see like the write commands, the MSM 6295 write. What I'll do is I will set an action on them, and you see, look, I put word value and just the bytes of this, right? This word value, right? Because in this game, 68K actually interfaces with the O key, and so the 68K has a 16-bit bus. However, the O key has an 8-bit bus, right? So I'm only interested in the lower 8 bits. Okay, that's what this does. And what it'll do is, what I'll do is I will basically advance to the point in the game. So I'll just show you right now, real quick. It's a very useful technique. I do this all the time for various things when I want to get the data out. Okay, so load in, let's see, load in Truxton to, here we go. All right, so I'll clear this. How can I do this so it's more productive? Let's see, make this smaller maybe. All right, so you see there's already output here. All right, so you see like all the commands get outputted in sequence in the output window, and then I'll just like take that and I'll work with that. Okay, so that's that, and then there's a couple of different things I want to show you with this too. So that's your test bench, right? And then you have the X6295 at the bottom for the unit under test. Okay, when this outputs data, right? It's going to be in like sort of a text file, and so like there's a certain format to where I output it, and then I have a Python script that actually converts that to a WAV file. Now, when I have a WAV file, I can take a look at that in Audacity or something, and I can inspect the waveform. So that's what this does. That's what this Python script does, is it converts the PCM raw data that I got from the test bench into an actual WAV file that I can listen, and I can change the sample rate here to suit the game. This is just happens to be the one for the bat writer, and there's other games that have different sample rates that I can put in there. And I'll just run the script, and it'll generate a WAV file, and the WAV file I can output. Okay. So I think that's about it. That covers just about everything in terms of the 6295. Yeah, I will release this. This is the one that we use across all of our cores at the moment. We haven't finished swapping it into every single core yet, but this is the one we use now. Nowadays, we use this 6295 that was built in house. And so we will release this and other sorts of modules. Probably in a few days. I think I think for the past couple of weeks I've been working on educational material largely. Like this, I mean, this sort of video is also educational material, but like other sorts of educational material, documenting things. So we're preparing to release, quite a bit of that sort of thing, like sample code and that sort of thing. So stay tuned, and let me know if this is useful to you, or if you have any other questions. I'm happy to answer. Okay, thank you.